go into the next one, Polyjet from Objet. They have a line of full cure material. As David told you, it's very much like an inkjet printer, where you print the curable resin and then expose it to light at about 15 micron layer thickness. They have a couple of series. The full cure material, just for general purpose, and then except for ones that are adapted for hearing aids. That's one of the things that really makes this turn this into a regular manufacturing area. That's the bare materials, which are opaque and very strong, comparably strong, varies gross exaggeration. And the technical materials, which are very flexible. The Tango Plus has the highest flexibility of all additive manufacturing materials, with a stretch to break of about 218%. Yeah, and we talked about, David was into this, is 3D printing really rapid manufacturing? Mainly for visualization, but on the other hand, well, some objects just have the property that you want to look at them, like if they're made for decoration, like a bulb. Then that is can use to look at it and it looks nice. And also, of course, a lampshade. But that is for the C-Corp materials. They have a number of different powders which can be infiltrated with different kind of resins, and then you can achieve different kind of material properties. Like the powders could be foundry sand, plasters, starches, and can be infiltrated with cyanide and wax and elastomers and other materials. And then there's voxeljet, which is basically use acrylic, especially more acrylic, which is fused to use a solvent, dropped in print, and then infiltrated with epoxy resin. There's a little more towards real manufacturing pieces. Metals. I'm a metallurgist to begin with, so I can talk about this for hours. I won't, not today. As I said, indirectly you make a mold, then you don't really, the material properties is not really bound or limited or characterized by your additive manufacturing technology. So it's when you add it directly. Gas, well, liquid is the really interesting first really interesting one of them. Selected late melting material, I would argue that that is micro-welding. Always just melt material and add on small micro spots. And then of course you can make a difference between if it's selected melted material in the powder bed or if it's material injected into the melted substrate, which is what I call powder injection process and selective melting. These are basically very, very much alike. LASIK using EVM and SLM are just different names for almost the same process by different vendors. Concept LASIK call their process LASIK using Arcan, okay, they're different. They use an electron beam, which makes it a little bit different, but otherwise it's a different energy transfer. That's the difference. Electron beams are more strongly absorbed by metal materials, have not that same reflecting, does not reflect, or at least absorb more energy than a laser does, which makes it a little bit different. Otherwise, SLM, selective laser melting, that is more or less the same as LASIK using, you just melt some powders in a powder bed. I added here EOS M2 and the 70. EOS themselves call that DMLS, but they call all of their metal applications DMLS. And in M2 and the 70, that is not what's happening. They are melting the material. DMLS is short for direct metal laser sintering, and that is sintering material. It's liquid phase sintering, or what I call it really three-dimensional brazing of parts for that kind of thing. MCP Heck were the first who were the one who first took a patent on the SLM, and that's why it's such a confusing about what names are developed. Names are different than the species. Material injected, these three are also very much the same. Lens, DMD, and LC. There's, well, you take a look at them later. They call it laser cladding. DMLS from EOS, that was the first direct metal process that was on the market, where I actually have powders of different melting temperatures. One fraction of powder, about 30% is melted, so it's basically brazing. They only can use about two types of materials on the market right now, and I think it's slowly leaving the market. Then we have from solid materials, we have the SLS, basically an adaptation of plastic processes, and 3D printing, which is also an adaptation of 3D printing process, but then you need the secondary process of furnace, where it's sintered and infiltrated. Okay, 5 minutes, that'll be fast. We talked about this one before. There are several processes for selecting melting material in the bed. I think I covered most of that. There's there are varieties of steel, aluminum, titanium, nickel, cobalt-based alloys. Selected laser melting, laser using concept laser. Their approach is, I could say, quite German, very orderly. You get this material, you have these process parameters, and you will get these material properties, very structured. If you do anything different, you will not get the material properties, and they don't guarantee anything. That's actually quite different from the next one, this MCT. But they have developed a number of quite different materials, which are also very nice properties, comparable to standard materials. We have there's also an issue here, or point here, that this is very much developed for making tools with conformal tooling, so they have gone most into different kind of tool steels. MSP Heck has a different attitude when it comes to materials. They tell you can use just about any available materials. They don't guarantee anything, but if you do well, please tell them. On the other hand, you have no guarantees. You're on a large extent on the road. They have a number of different alloys, and of course you can't be very strict about what you have. EOS is something, it's a little bit like conservation attitude, and they don't actually really, not that liberal in giving away the material property data. I've tried to get it from them, but they won't give me. One of the reasons is that and they're right about that, it very much depends on what kind of process parameters you use. They can change very much, and that's the same thing in all these additive processes. And in part of their strategy, if you want to gain time, you can use different kind of process parameters in the part of your build, so that you save time, but then you have different material properties there, of course. That's another thing. They do quite well in the material properties, are what I've heard, is all very good for the full melt materials, like the stainless steel, the more aging steel, gold, chrome, and titanium. And then they still do have the direct metal direct steel, other versions of these three-dimensional brazing systems, which had a melting fraction of the powder and a non-melting fraction of the powder.
Stuart Jackson from EOS is here, so if anyone's got specific questions about EOS, I'm sure Stuart will answer questions. At the top left, stand up, Stuart, so everyone knows.
You probably kick me later for saying what I said at the moment.
I 100% agree with what you said.
Sorry?
I 100% agree with what you said.
Thank you. That's relief. Then there's Phoenix, French system. They are not that liberal with information from the website, but they seem to be doing quite well. Also weldable materials, use ceramic powders too. Have a number of different metals. Mechanical characteristics are very close to machine parts. That's the answer they got. Most of the selected laser melting based processes, powder bed processes, have material properties that are similar or better than as cost materials. Some, like Archem, actually exceeds forged materials. That's basically because they have this powerful energy transfer, and they melt and remelt each layer in a number of times. They also have no layering effect in material properties. On the other hand, they get a coarser surface.